Our next speaker is Arushi Nath, and she'll talk to us about open source photometry algorithms.
Hi, everyone. It's so great to be presenting here today. My name's Arushi, and I'm a grade 9 student from here in Toronto. And today I'll be talking about how I created algorithms in Python to look at exoplanetary systems. But first, a bit of background. For the past couple years, I've been really interested in planetary defense. In particular, last year, I've been working on creating algorithms that determine the physical properties of asteroids, like how fast they rotate, their size, and so forth. And last year, especially 2022, the Didymos was a very interesting asteroid because it had just been hit by NASA's DART mission with the goal of testing the kinetic impactor method of deflecting an asteroid. So this had provided me with the perfect opportunity to apply my algorithm to determine the physical properties of this binary asteroid Didymos and see how it changed after the impact. And this project was very successful, and I was able to measure several physical properties of the asteroid, like its absolute magnitude, its rotation period, the orbital period of the moonlet, and its size. And this was really fascinating for me. And it was amazing to have my project win the top award in Canada. And in addition, I got to present my project globally at an international science fair, where my project got to win the second core prize. But honestly, I think the best prize here was actually winning the 2023 Youth Astronomers or Young Astronomers Award from the Royal Astronomical Society of Canada. So I would like to say a big thank you to RASC for providing me with this award. And now that I've done this project, I want to apply these algorithms that I created to go from asteroids to exoplanetary systems. In particular, I was very interested in exoplanets which follow the transit method. This means that when the planet goes in front of its host star, you will be able to observe a dip in the light coming from the star as the planet blocks some of it. This creates a dip in the brightness. And by observing how much this dip was created, you can see the ratio of the radius of the planet and the star, which can lead you to find the size of the planet itself. But it gets more interesting because these exoplanets also have atmospheres, and these atmospheres react differently in different wavelengths. For some wavelengths, it absorbs light, and in some wavelengths, it reflects light. So by measuring these exoplanetary transits in different wavelengths or different filters, you should be able to observe different dips in brightness. And this is actually what many space telescopes are already doing. For example, NASA's James Webb Space Telescope and the upcoming Ariel telescope from the European Space Agency, which is launching in 2029. And these telescopes have these very high precision spectrograms, which are going to observe these exoplanetary systems. But time on these big telescopes are very limited, which means that when these telescopes are observing an exoplanet, we have to make sure that this is the best possible use of our time, which means we need to know exactly when the transit of the exoplanet starts and when the transit of the exoplanet finishes. But some of these transits are still not accurately known today. This could be because their periods are very long. For example, the exoplanet takes over a year to orbit its host star, or simply not enough observations of that part of the sky has been taken. So, to improve the ephemerides of transit, we heavily rely on citizen scientists. And I wanted to help with this. So I sent a few robotic telescope proposals to different observatories around the world. For example, the Bergafne Observatory in Canada, as well as a few others around the globe. These telescopes don't need to be big. Actually, the smallest telescope that I used was only 6 inches from NASA's Micro Observatory. In addition, I even used my own telescope to set up a few observations. So, if you've seen my past presentations on asteroid photometry, you'll notice that some parts of the methodology are quite similar. For example, the first part is finding all known stars in the image. To do this, I used European Space Agency's Gaia database. This allowed me to find all of the known stars in my field of view. I then centroided these objects in my image using simple mathematical formulas. But now I wanted to actually find the brightness of the exoplanet and see how it changed over time. So to do this, I created apertures of different sizes around the exoplanet. I created an inner aperture, and this was to measure the brightness of the exoplanet itself, as well as an outer analyst to measure the background noise. Subtracting the two would give me the pixel brightness of the asteroid. Finding the right size of the aperture was complex because you didn't want it to be too big or would contain too much background noise, and you didn't want it to be too small either, otherwise it wouldn't contain the full object. So analysis and modulo to find the right size. Next, comparison stars. Because exoplanet transits are long, which means observing conditions will change during this time. So to account for these, I used comparison stars to benchmark the brightness. These comparison stars couldn't just be any stars. They had to follow three main parameters. First, they had to have a similar brightness to the target star. Second, they had to have a similar color to the target star. These made sure that we were measuring stars under the same parameters. And finally, the stars used as comparison stars could not be variable, and this is essential because otherwise these stars would have fluctuating brightnesses and ruin everything. So then, by measuring the brightness of these comparison stars in the image, I was able to apply these to the target star, in this case, the exoplanet. And after this, I was able to get some outputs. I was able to create the light curves of several different exoplanetary systems. For example, TRES-3b and the WASP-12b. And an observation isn't complete unless you know it's accurate. And my results were able to get validated by the ExoClock initiative, which is from the Aerial Space Mission. And I was able to submit my observations, and they were accepted, and they're now part of this global database. And this project is far from over. I've plans to continue building up upon my photometry algorithm, and then perhaps even try to use ground-based telescopes to observe these exoplanets in different wavelengths to see if I can measure any differences in the transit depths. So with that, thank you very much.
Thank you very much, Arushi. More excellent work coming from you. Keep it up.
Thank you.
Do we have any questions for Arushi?
We have a comment and a question from me. From Guyanis says that this young girl is amazing. People like her will contribute to a better planet to live on.
So much.
Congrats. And my question is, while you were processing your data, would you happen to have come across any unknown variable stars?
Yeah, that's a great question. And while so far, no, that's definitely a possibility, especially because you're observing the same part of the sky for a very long period, which means that if there is a variable star, then it'll definitely come out. So possibly after I use my algorithm on many different exoplanetary systems, possibly one of the comparison stars I use might be faulty, and looking into it, it could be a variable star, but not so far.
And may I ask, as I've asked in the past, are you publishing any of this in a Jupyter notebook or related?
Oh, definitely. Once I expand this algorithm, I will definitely be posting it on my GitHub account as usual.
Fantastic, thank you. And that's all the
Great,
questions.
thank you so much.
Thank you, Arushi.